Today we are going to review a little bit about multivariable level curves. Did you all watch the cake video? Was that helpful?
Yes.
Cake, yeah? I'm hungry. I wish I could bring cake, but it would be like one ESG class per row. Okay, so we'll review that, and then I want to talk about directional derivatives and spend a little bit more on tangent plane. Real talk, yes. Who could? Whoa! I think I have my answer to the question. How would you feel if you were asked to derive the equation of a tangent plane for something on the spot? Who's good? Okay. No one will be offended if you're not.
Do we have our notebook?
You do not have your notebook. You have a pencil, a bottle of Gatorade because it's hot, and that's all. And a writing surface. Okay, so we'll review some of that. So, but fundamentally, let's just talk about the following. We have some function in three-dimensional space, and I tend to like paraboloids. They're pretty, they're easy to draw. Yeah, they're very non-polarizing. All this stuff in chemistry. Okay, so here's our paraboloid, and a function in two variables that get you this. Z is f of x, y. What have we seen is the general equation for a function like this?
X squared plus y squared.
You got it.
Yay!
F of x, y is x squared plus y squared. Oh, right, fun. And that's all very pretty, and there's a bunch of different approaches you can take to it. The one I want to talk about for the moment is the level curves, because you all are pros at level curves. So what do the level curves of this function look like? Circles, right, of increasing radius, yeah, and the radius increases, I guess, x squared plus y squared equals c. And so you have circles in it. You all go to circles. You'll do like tetrahedrons or something later on in chemistry. So these are our level curves, and what is the direction of increasing f, increasing z?
Upwards.
Upwards, right, like this, yeah. So this could be like z equals 10. This is maybe z equals 1. Right over here we have z equals 0. So we know that we can reconstruct our shape, and I had some fun with the laser cutter, and I'm going to pass this around, but use this to practice reconstructing the shape from the level curves. Each of those is a level curve. Well, the outer ring of it is a level curve. So if any of you took AP Human Geography, you talk about terracing or something. I don't know why, but I think of that when I see this. We can all be farmers. Okay. Yeah, so that's one way. And again, in the spirit of what's being passed around, you can, in fact, if you have chalk, draw this in three-dimensional space. So if we have x, y, z over here, we know we have a point here, we have a circle here. Now, there's a bunch of different shapes whose level curves are concentric circles. Also, we are recording the class, so say hi to your future selves. Hi. Hopefully they know better than you do, for I wonder what reasons. There's a variety of different shapes that have concentric circles as their level curves. How do we know the pattern of how these circles grow as you go up in Z? Anyone want to, throw something at the wall? Figuratively. So you could do gradient, you could do partials. I'm going to go with something even more straightforward. This is taking slices in x, y to see how z increases. But again, like, what are some shapes that can have circles of increasing size as you go up in z? Oh, you could have a cone. You could also have a paraboloid. So how can you tell the difference? What was that? How fast the radius increases, right? So this isn't, something meant to keep you up at night. Certainly you already have enough stuff to keep you up at night, but it's more like, think about it. We're going to see how the radius of the circle increases with z. What's the radius of a circle?
1.
Or in general? It's z. So, and what's this, x squared plus y squared? The radius squared, right? So the radius, z is proportional to the radius squared. I guess what kind of shape does that start to look like? It's a parabola, right? Like you got something like, so yes, odds are, what I'm really trying to say is this will go whee in place of like a cone. Does that make sense? Okay. This is a thorough analysis, and you needn't go that far most of the time. Say this when we go polar coordinates. Yeah, bring all your Canada Goose sweaters when we go polar. But that's another time. You have a joke. You have a button for labored laughter. That would be a good time to press it. Okay, so here we go, and these are the level curves, and we get our function. That's all very cool. But there's something else, because we're in multivariable calculus, and you don't take a derivative, you're not for real, right? So let's take a derivative. What kind of derivatives are we taking when we're in multivariable calc? Partial derivatives, yeah. That doesn't mean a half-assed derivative, it means just in one variable. So what is d by dx? Also, notationally, this is the same. I don't know that I've said this in class. I know I haven't. This is f sub x. It doesn't mean the x component of f, because f is a function, it's a scalar function. It means the x derivative. So when you put a subscript with a variable, it's the partial in that variable. And what does that mean in English? It's going to be a pattern here of doing things in English. Changing the x direction, right? And what do you do with y? Keep it constant, right? This is like you're trying to adjust some screws on some washing machine you're trying to reassemble. Tweak one variable at a time. You're never going to get your washing machine back together otherwise. I don't know why I'm saying this. It's not like I haven't been hurt before assembling a oh, I have stories. There was a pipe in my property that broke, and that pipe carried the sewage of the entire street. So even though I told my tenants to stop showering and pooping, it didn't matter, because poop still came out. Somehow that's related, right? One variable at a time. I didn't have control over the others, so I couldn't take partial derivatives. Okay, so notationally this is this, and this all coalesces into a beautiful function called the gradient, the grad, yeah, with the grad, with the cap, right, the graduation cap. The gradient and that's just f sub x, f sub y. I tend to like doing this, it's just less to write, but again, we know that notationally that's the same as df by dx, df by dy. Okay, so what are we going to do with this to be useful in this world? We are going to, well, we're going to calculate it, but we're usually using this to do something else, usually in the tangent plane world. So first off, are there any questions on partial derivatives and level curves?
Is it going along the surface then, or is it going outward?
Oh, the gradient?
Yeah.
Excellent question. So that's going to be my next thing to go. Thank you, Noah. All right, more questions. And where are the level curves? Where are they in the journey through the room? I mean, all the way back up.
Where?
Okay, and there. And that's. Are you? Is it going? What's the velocity vector? Yes. Okay. Cool. All right. We know that that's perpendicular to the gradient. So actually, Noah, let's talk about that. Because there's a lot of ways that people can make messes with this. So the gradient. Well, first off, f of xy, or any function, if you have more variables too, let's say z is f of xy, is a what valued function? This is a new way to talk about this. Something valued function just means what kind of thing does the function give you? Ooh, okay. And then, wait. And then grad of f, which is df by dx.
Oh,
df by dy. Aha, lecture theory, right? Is a valued. Okay. So you want to fill the blanks in now? We're feeling brave. Everyone's brave until the cockroach they're trying to kill starts to fly. What do we have?
500 for scalar.
Yeah. Okay. But which one? You can say.
Oh.
Yeah. No, I know. I'm trolling you. And then this one is a vector valued function, right? You can have matrix valued functions. You can have, whatever you want. But this is worth knowing. So the function itself is a scalar. The function, you give it an x and a y, and it spits out a scalar. The function, you spit out an f. The gradient, you give it an x and a y, and it gives you a vector. Does that make sense? Cool. So a scalar value function is a scalar at every point. A vector value function gives you a vector at every point. And this is really cool when we talk about vector fields, but I'm not going to dwell too much on that. Instead, I'm going to talk about Noah's question, which was.
What does it look like on a graph?
What does it look like on a graph? Okay, and that depends on how many dimensions you do it in. So I now need to spend a little bit of time cleaning something up before you can have a chance to see that it would make a mess otherwise. And this is not a luxury I normally take during the semester. Because I don't know why actually. Why didn't I fix it? I don't know. But I'm going to make it right now. So generally, we have two ways of writing a function. We have explicit which is, what does it look like on albums? Explicit. Parental, you know what I'm talking about?
Yeah.
Yeah, what does it say here?
Parental advisory requirement.
Parental advisory, okay. Okay. I read that as prenatal advisory, but that's not one. Yeah, no, pregnancy is not in anyone related to his future. So well, here we are. Okay, so explicit defined function just means z is f of x, y. And then we have instead implicit, which I don't have a cool thing for. And implicit would be f of x, y, z is equal to something, right? K, yeah, k, where k is a constant. Give me an example of an explicit function. We just did one, right? X squared plus y squared, right? It's z is some function of x and y, and it's this. So you map your height as coming from an xy coordinate. Does that make sense? Okay. There's a lot of places you will see these. Anyone interested in doing probability and statistics? Maybe? Probably? Yeah, Carlos, okay. So actually, that's exactly an example of an explicit situation. Is let's say that the likelihood, so this board that gets obscured is for tangents, but that are kind of relevant. So let's say that I set the probability as a function of your row and column number in the seating arrangement of the classroom is, I don't know, where do I have a really high likelihood of choosing someone who wants to learn about probability in this classroom? I thought so, but they've already replied. Oh, you too, say? I didn't know you want to learn about probability. Okay, so both in the front and in the back, right? So imagine that I have a function in 2 dimensions, x and y, that tells me what my likelihood of picking a probability person is. So you two raise your hands for a moment. Yeah, you two got this. Oh, he's got 2 hands. Okay, so his peak is bigger than her peak. That's fine. All right, but the point being that it is some variable as a function of 2 other variables. Does that make sense? Okay, that's the explicit case. Then we have the implicit case, which just says that some wilder relationship between the 3 variables is equal to something. So this would be an example. What is the equation of a sphere? So z squared equals, let's say, 4. Okay, this is an example of an implicit way to express a function. And who's to say I can't write it in an explicit way? How would this look like an explicit line? Yeah, I trust you all. Again, you were all presidents of the solving these equations for the other variables club in high school, I'm sure. So this is z is plus minus is 4 is square root of plus minus square root of 4 minus that stuff. Yeah. Okay. In both of these cases, though, this is what we've got. There's a reason I wanted to talk about this. Oh, dimensions of the gradient. Yeah. So let's take the gradient of this. What is the gradient of this? Okay. What is the gradient of this? This is now gradient of f of x, y, z, and it is what? And the thing that usually comes up that people are like, wait a second, Christian, and then I'm like, oops, yeah, I've been lying to you this whole time, is that I'm not going to lie to you. You don't want to develop trust issues this early. So we're going to change this instead to writing this explicit case in implicit form. And in implicit form, there's 2 ways we can write this function. We can say f of x, y, z is equal to, can you all see this? Yeah. F of x, y, z is equal to, well, actually, what are 2 ways I can write it?
You can move something on the other side.
I can move z to the other side, so I can say it's f of x, y minus z, which in this particular case would be x squared plus y squared minus z. And on what's the right-hand side of this guy, by the way? When I move everything to one side. 0, right? But there's another way I could do it. Or I can do z minus f of x, y, which would be what? Z minus x squared plus y squared. Okay. And then from here, what can I do? I can still take a gradient. I mean, I'm going to encroach a little bit on here. But this division will hopefully keep us sensible. So what's the gradient in this case? Let's just do it here. Now our gradient is not in 2 variables, it is in 3. So we have grad of f of x, y, z. It's what? 2x, 2y, and then what goes over here? Careful there, because it's a df by dz. -1, yeah. All right, person who said 0, you feel better? You got to people above it. I appreciate the bravery. Well done. Okay. So I guess a couple of questions come in, which is why do we use this versus why do we use this, and what directions do things point in? And I think a really useful way to do this might be to talk about the p set and that really awfully worded problem number 6 that I borrowed from last year's p sets, and after hearing your reactions to it, we'll rephrase for next year. Sorry. I don't know, it's because you guys were still subjected. But what did problem 6 in English ask us to prove? Yeah.
That was the one asking us to prove that they were perpendicular, right?
What was that?
Perpendicular one?
Yeah, prove something perpendicular. Do you remember what it proved? What I asked you to prove?
The gradient vector and the actual derivative of the surface.
Yes. The gradient vector, the gradient is the derivative of the surface, so hang tight.
The level curves.
Yes, the gradient is perpendicular to the level curves.
Yeah.
The gradient is the direction of steepest ascent. And to do this, I think we got to play Fortnite. So I brought this up to, who here plays Fortnite? Okay, I like the unapologetic nature of this guy. I bought my sister a Nintendo Switch in 2018, and I then took it away just so I could play Fortnite. Okay, and in Fortnite, what was that? Someone explain Fortnite for me. You're all better at this than me. Oh, what do we know about Fortnite? What happens in Fortnite? What's the mechanic game? Okay, you got dropped off from a floating school. You speak up, William. You got it.
Oh, okay. And then
No,
like,
but stand up.
oh no, it's okay. Yeah, I'm fine. And then like start like.
Okay, so you're dropped off by a school bus. You start killing people, and what's the twist? What's the exciting thing?
The storm.
There's a storm, right? And the storm, if you're in the storm, you're screwed because it'll kill you. So the storm shrinks. And normally what you see is the following. When the storm is about to shrink, you get told that this is the safe zone. And odds are you're not there. You're here. So you get shown a map. And does anyone remember what else gets shown on that map?
The line.
A line from you to the safe zone, right? Okay. What direction does that line point in? Ah, right, because why couldn't it just point here? This is a way to get to the safe zone. It's further apart. The whole point of that line is it tells you, hey, you want to get here fast, and the fewest number of steps, you better go this way. Right? So it'll give you an arrow in this direction. Now the cool thing about this direction is that it is perpendicular. This is precisely how level curves relate to the gradient. This is your gradient direction. The gradient is the direction of steepest, what? Ascent. Steepest change in your function. So what direction does the level curve, does the gradient go if you plot the level curves of a function? So now we are in 2D, right? These are our level curves. Our gradient goes where? Let's say that we're here. So it's going to go perpendicular to here, right? Oh, yeah, steepest ascent, right? So let's say that z is 0 here and z is 100 over here. So this is rising direction. Okay, what direction does the gradient point once we're at this point? What was that? Yeah, that way, right? The pencil says it all. Okay, so there's the gradient. And then if we have one more little level curve, and it's kind of like the shape, this is my default level curve. It's like what's being passed around in the class now, then we're going to go here. Okay, this, believe it or not, is how AI works. It moves in the direction of the gradient. Well, it moves in the direction of the negative gradient because it's not trying to maximize something, it's trying to minimize something. And that something is error. Right? You train AI on a bunch of data, and you want it to get really correct at classifying the data. So you want to minimize the error function. So you take steps in the direction of the gradient in the parameter space of all the weights. It's a whole tune off this out, and I guess I'll turn it into a life analogy. Okay, questions on direction of gradient so far? you were there. Okay, my sympathy. Yes?
Is it going inward or outward?
Oh, you're thinking like 3D land now. You're thinking 3D, because there is no inner outlet for 2D.
No, like, is it pointing like outside the shape or inside the shape?
Oh, I see what you mean. Ooh.
And that one was going inward, but that one was going outward.
Yeah, it's a tricky question because I do think we have to be more careful about in or out. Like here, it means in, yeah? In is the direction of up. But in 3D, that gets very tricky. So I would hesitate there.
It moves in the direction it increases z. So in that one is using outward on the xy plane.
Right.
That one is decreasing the xy plane. See how it would be able to go inward to get a higher z? And on that one, you go outward to get a higher z. It only depends on your level.
Well, hang tight. Yes, you do have to go outward to get a higher z. You're right.
Oh.
And if this were concave with the other one, right? Then you go inward to get a higher z. Yeah.
It's like if you want to climb, that's where you gotta go.
Yeah. Topographic maps, basically.
I still don't understand why the gradient gives you the steepest descent, because like the gradient, you take the derivative like of z with respect to x and derivative of y with of z with respect to y. So why is it this?
Why does that give you? To do that, we need to talk about something called the directional derivative. Did you guys see directional derivative yet? All right. So directional derivative is quite cool, and it's in the schedule, so we ought to do it. Okay. So directional derivative sounds a lot more foreign than it actually is, because you have seen it in some capacity. All right. So I need all of you to visualize yourselves at the base of a mountain or something, and you're looking at the topographical map, and again, here are a bunch of our level curves. Okay. What I'm going to ask you is the following. You have footsteps that you take, and you take them in a particular direction. So we're going to start here. This is at point A, okay? And we're going to revisit the whole Fortnite situation. There's going to be a bunch of different directions that you can travel from here to get from this curve to this curve. What does that mean in English, getting from this curve to this curve? If this is height 0 and this is height 10, for example. Different height, right? So you're on a mountain, you could go this way, you could go that way, you could go that way. I'm going to draw a bunch of different trajectories, and we're going to kind of derive the value of the gradient. So this is one possible route, this is another possible route, and this in green is another possible route. Okay, and the quantity that I'm interested in is df by ds, where s is path length, i.e. number of footsteps. Okay? So, first things first. In this direction, what do we want to call this direction? Actually, let's give them direction vectors. Let's call this u hat, or let's make them unit vectors. U hat, v hat, and the green one will be supplied. W hat, which looks like a poop emoji, or no, something else. Okay, we're going to stop there. Okay, yeah, you're welcome. First thing, what's the least productive direction if I'm trying to get high? W hat, right? Why? Wait, what? What was that? Because I'm going around the, so if you think about it, if I take a step in the W hat direction, by how much is my F changing? That's the whole point of a level curve, right? So my delta F over delta S, maybe I change by 0 even if I go, one step. So it's 0. Does it make sense to you that delta F delta S, as that step size gets really tiny, that's my derivative, right? So delta F delta S is a fair approximation, right? Okay, what about in the orange direction? Here, delta F over delta S, what's my delta F if this is z equals 0 and this is z equals 10? 10, okay. And I'm going to use lecture theory and say that it took me 20 steps to walk from here to that height on the mountain? So what's my df by ds approximately? 1/2. Okay. Lo and behold, here's my gradient. You can see geometrically that this is indeed a shorter path. And you can imagine that because it's a shorter path, again, in the yellow direction, delta f by delta s, we're still going to have the same change in height. But let's say that we have to travel only 10 steps. So that's 1. So 1, 0, and 2. Of course, we have to underline them in the same color as we wrote them. Okay, so where do we get the most bang for our buck? In this direction. Now you can prove, because I think I am being a little bit loosey-goosey about certain things, but you can actually prove that this quantity, df by ds, which is called, as fate would have it, the directional derivative, is maximized in the direction of the gradient. Okay? So let's do a little bit more, just to formalize it again, directional derivative. I feel like I'm being less messy on the board now. Maybe it's because there's a camera here. I don't know, that's weird. Hello 2010 Scalar-Valued. All right, so what do we have? We have df by ds. What do I need to know in order to find the directional derivative? What was each of these calculations contingent upon? I need to be given a direction, right? So very formally, I need to say this is the directional derivative in the direction of a vector u. Okay? And notationally, they also call it the Duff. And the Duff, I'm going Patrick on this, I think certain words louder, is the component, what do you think? Components in the direction of, yeah, ooh, okay, is it possible that I'm making a mess now? This is the wait, oh, I know my stuff, give me a second. How do we brain from it? Make sure I don't preview the wrong component. But what are people's intuition? If the direction that maximizes it is the gradient? Is it? I guess I didn't write something about direction. All right, give me a second. That'll be fun. Directional. Okay. The direction okay. Yeah. Okay. Which of these vectors is the strongest, most bang for the buck? And what is direction does v hat pointed? Yeah, I mean, spoiler alert, right? It's the direction of the gradient. So this is going to be the amount of the gradient in the direction of u. That is to say, it is gradients of f dotted with u hat. Why is it in the direction of u? I think I got to do a derivation for that one. So hang tight, Luann. Not another worthless endeavor.
Okay.
But so let's just rationalize, make sure we're not crazy. If u points in the direction of the gradient, what is this?
Wait, doesn't this give you a scalar answer?
Yeah, which is okay. Oh yeah. It's not a gradient. It's not a vector. It's a scalar. If u is perpendicular to the gradient, it gives you 0. And for all values in between, it gives you something. Oh, what if you're going in the direction opposite the gradient? Negative, yeah. I want to think about this. It's the amount of the gradient in my direction. Why is it not? You asked the question, it is a good one. Say it. Oh, it is. Oh, no, sorry. Okay, I see your question. Guys, this is for a general vector u. This is not, okay. For a direction u that you provide.
Oh, okay.
Not related to this at all. That was the question? Oh, okay, cool. Okay, so for a direction u, any direction, the directional derivative is this, and it is, again, the change in your function for a given change, for a given step in a direction of u. Okay. Everyone good? Okay, so that's directional derivative. And there was a reason I wanted to talk about directional derivative. Oh, well, if you go back to Fortnite, that's the idea. You know, one of the math class did, is if we go back to Fortnite. So this direction is the one that minimizes the number of steps you need to take to just get to where you need to go, which is the escape zone. It's your next big level curve you want to do. Okay, so that covers directional derivative, that covers partial derivatives. We need to talk about the tangent plane. Yeah? Okay, so let's talk about the tangent plane. And before that, I will throw one thing. Let's go back to talking about the gradient really quick. What do I want to say about the gradient? Gradient is very cool. I think this will be useful once I actually get talking about good. So let me stick to my original plan. The original plan is going to be to erase this board. Did you guys got this? Yeah, stop me if you remember erasing. Just look up horrified. Like, oh my god, I was copying that down. You see me erasing it in slow motion. Dramatic music is playing again. Okay. Very cool. Tangent plane. You all remember the cake? Who did not watch the cake? I won't be offended, I just want to know. Okay, so I'm gonna wait, raise your hands again, because it could be it's a sizable chunk if you. That's okay. Ain't nobody got time for that. But if you do got time for that at some point, do look, because I think it covers this smooth enough. In general, we're gonna have a surface S, or some surface, I'm not even gonna call it S. Some surface, and it's going to be defined by a function. Z is a function of x and y. And what do I want to know about this function? I want to know the equation of the plane that's tangent to it. So I want to go at this point, which is P0, which has coordinates x0, y0, z0, and I want to draw a plane which is tangent to that surface. Yeah, I did it.
No, I was going to spoil it.
Oh, what?
I was going to spoil it.
Oh. You were going to, in one fell swoop, you were going to spoil this?
No, I know,
think that's not worth
because you were like, I think I know how you do it.
Oh,
I
okay.
was gonna ask you that.
Got it. Oh, I see. Okay, yeah, so then better hang tight. I thought you were going to like deliver a one-line zinger that was somehow, because then you just, give me that and I'll put it in the notes. That's pretty cool. All right, yeah, like cheese or no beans, and then you're like, oh, now that makes sense. Okay. That'd be funny. We could have someone visiting and just confuse them. I bless you. All right. And by bless you, I mean, let's take the partial derivative of this with respect to okay, so a plane, that would be a way to confuse a visitor, right? If I taught high school, I'd totally mess with them. So, yeah, I don't tend to take myself too seriously. Let's finally do this. I'm talking too much. All right, so we define a plane. What do we need on the plane? 3 points or 2 vectors, or a point and a normal vector. We only have the luxury of finding out 2 vectors on this plane. And the way that we're going to do it is we're going to take slices of this function in the xz plane and in the yz plane. And if we do that, our surface in the xz plane looks like this, and our surface in the yz plane looks something like this, which is very similar, and that's okay. They're a little different, and they spot the difference. And what I'm going to do is I'm going to look at that point of tangency, x0, y0, z0, and I'm going to look at the slope of the line tangent to my curve in each of these slices. So I'm taking slices along these directions. Is that clear to people? On the x direction, I'm thinking this is why the cake comes in handy. Maybe this will motivate you to watch the cake. And on the y-axis, on the yz plane, taking slices like this. Does that make sense? When I take those 2 slices, I'm going to have 2 tangent lines. What are the slopes of these tangent lines? What's the slope of the tangent line to the xz slice is df by d x, and the slope here is df by d y. So now here's a good question that I think was in some way in the piece set. How do I write a line of this slope in vector form?
Anytime it's one in the x direction.
Uh-huh.
And you're not moving the line.
Brilliant.
You move in the dx direction.
Did you watch the video?
No.
Cool.
Yes, I did. For the
No, it's fine. It's awesome that this is, because I'm just pulling this, off the cuff. All right, wait, say again, Mike? Yeah. Sorry, that's a good point. This is this vector. Does that make sense? Say again? So df by dx is a rate of change, right? So for each step in the x direction, f changes by df by df. Okay, take the slope of a line. If the slope of a line is 2, for each step in the x of 1, by how much does y go up? If the slope of the line is 2. 2, right? Rise over run. Right? Well, the rise is the z, and the run is the x. Rise over run is that gives me that slope. That's a good way to do it. All right. I just figured this out. I figured this out as a way to teach it. All right. So can someone follow me down this path? Someone new. Hi, sibling. Can I pick on you? I appreciate that. Okay. So now, what's the slope of the sign? It's df by dy. So what is the vector that points in the direction of the slope from here?
Could be 0, 1,
Uh-huh.
f, and y.
Yeah, df by dy. Beautiful. Does everyone understand why that is? 1.
Why do we have the 1 again?
What was that?
Why do we have the 1 again?
The 1, so the 1 is a step in that direction. So if we have a 1 in the x direction, we're taking a step in the x direction of 1. And slope is rise over run, right?
Yeah.
So as long as rise over, this is not the only way you could write it. You could write this as df and write this as dx, but this is what you have to find in the rules. All right, questions? Bon, you good?
Yeah, good.
Okay, very cool. Hey guys, we have 2 vectors on this plane. What do you want to do with them to find something useful? Cross product! I promise that when you find the cross product, let's just do it. So we know that the normal vector, is it a unit vector? Not necessarily, we have no idea. We just know that it's a vector normal. It's not a unit normal vector, so it's the cross product of this one and this one. So 1, 0, fx crossed with 0, 1, fy. Everyone comfortable with me using the subscript? Yeah?
Yeah.
Very cool. That's I hat, j hat, k hat, 1, 0, fx, 0, 1, fy. You guys been doing determinants in your sleep lately? Nah?
Yeah.
Nah, that's okay. The redhead has filmed me falling asleep and talking about math so many times. Like the null space, and I'll have to pull them up, but like I would do this in my sleep. No, I'm not saying that I'm agile, I'm saying that I have nothing better to dream about, I guess. Alright, so what do we have? We have a negative fx. What's the next one? Negative y. And the last one? 1. Yeah. By the way, how many ways can this normal vector be oriented? 2, right? So I think I just gave you this one, but I could also come up with this one. It's fine. So I could do this, or if I had the other order, right? 0, 1, fy crossed with 1, 0, fx. So we'll have or fx, fy, negative 1. You all believe me that that's what would happen if I flip the order? Oh my God, we're in really good shape, because if we have the normal vector to a point, to a plane, we can come up with the equation of that plane. Can someone go ahead and fill us in on how to fill this in?
Well,
Yeah. So equation of a plane in general.
and r naught is equal to 0.
Yes.
We're talking.
Yeah, because the normal vector n dot a vector pointing from p naught to an arbitrary point p on that plane is equal to 0. We agree? Well, basically, normal to the plane is perpendicular to vector on the plane. So that's, and I'm going to use the positive ones. Df by dx, df by dy, negative 1, dotted with x minus x naught, y minus y naught. z minus z naught is equal to 0. All right, algebraic gymnastics, what are we going to get? df by dx times x plus df by dx evaluated where? Sorry, this is important.
At your point.
At p naught. So this bar with the p naught next to it means evaluate this at p naught. Just like directional derivative with the bar, evaluate that at that direction. So df by dx at p naught times x plus df by dy p naught times y. What happens with our z situation? Yeah, minus z is equal to, e. Move all the other constants to the other side, which you can find, right? It's what is it? df by dx at p naught x naught plus df by dy p naught y naught, and then what happens with the other one? Plus z naught, right? Y plus z naught. There's a 1 in here, right? Did I do this right? Yeah. I just moved all the constants to the other side. Wait, is it a plus z naught or is it? It's a minus z naught.
No, it's a minus in unit to the other one.
No, it's a minus. I insist because I'm happy to question my algebra, but I think I remember.
Yeah.
Because in this particular case, because it's a minus 1 dotted with a negative 1, and then you move it to the other side, so that positive became a negative. Okay, are we all good? Okay.
Comes from.
So that's the equation of the tangent plane, which means to find the equation of a tangent plane, all you need is, if you have the function, what can you find?
Partial derivatives.
The partial derivatives, which gives you the gradient, which informs this. Beautiful. And then you have a point on that plane?
Yes.
Yeah, because we asked you to find the tangent plane at a particular point, right?
Yeah.
So you plug in that point. Okay. What else does one do in algebra, or in calculus, single variable land, is once you have the equation of the tangent line, you can do all kinds of pretty things with it. Approximation. This equation carries more punch than you guess initially. And the reason that it carries more punch than you would guess initially is that if I just focus for a moment, I'm going to pick on writing it this way. This looks like the following. df by dx at p naught, x minus x naught. This is before I expand the, before I do my distribution. Plus df by dy at p naught, y minus y naught, plus, what do we have? Or minus 1, I'm going to put in plus negative 1, z minus z naught is equal to 0. Is this correct? Okay. Single variable calc for a moment. Here's y equals f of x. If I have my tangent line equation at a particular point, x naught. What was that? You said Taylor series or something. Kind of like it, yeah. Well, I'm going to do the very first term in the Taylor series. I'm doing a linear approximation. For small deviations, delta x, so this is x naught plus delta x, and this deviation is delta x. For a tiny deviation, you can figure out what the function is, not by using the actual function itself, but by using the tangent line, right? Tangent plane is the same exact idea in 2 dimensions. Think about it. This x minus x naught, what can we call that? Delta x. So partial with respect to x at p naught, delta x, plus partial with respect to y at p naught, delta y, plus this we're going to spend some time unpacking in a moment, z minus z naught equals 0. You can use this to solve what z is when you're starting at a particular point and you're changing by an amount delta x delta y. You're trying to figure out how much your z changes. Okay, does that make sense? Yeah, Mon.
Could you review, how did you do the cross products on the
Of these two?
Yeah, those 2.
Yeah, determinant of the 3×3, right?
Yeah, that's,
Yeah, eyebrows. Well, well, mini eyebrows, because you do remember I hat, and then you take the determinant of the little submatrix,
yeah.
minus j hat, determinant of the submatrix, plus k hat, determinant of the submatrix.
Where did your negatives come from?
Where do my negatives come from? Oh, because look at the determinant. If I have I hat in the crosshairs, right? I have 0 minus
Oh, yeah.
df by dx.
Okay.
But do you understand why there are really two normal vectors?
Yeah, I got it.
Yep, so it could, if I switch the order, I just get a negative instead. Because the cross product, so the dot product doesn't care about order. Cross product does. The cross product, if you flip the order, is just what? The insurrection, think about right hand rule, right? U cross V versus V cross U. Yeah? Oh yeah, bunch. Well, I was just thinking about one too, but I don't know what to.
Like how we solve for change in
You solve for change in Z. Yeah, so if I said that I'm at a particular point, x naught, y naught, z naught, and we have a function, you can find the partials. You know about how much x is changing, and you know where you started, so you can solve for the new value of z.
so you do the change in
Yeah, because let's say, so the way these kinds of problems would go is, example, say f of xy is square root of x to the fourth plus y to the fourth. Someone's seen that one before. Find f at 1, 1, and the tangent plane at 1, 1. And then the next part of the problem might be use the tangent plane to approximate f of 1.1, 1.1. Tiny deviation about the point of tangency. Make sense? And you looked really confused for a moment then. Did you eat warhead candy? Or can you cut us? It was warheads or something. Oh, has anyone read the Amazon review of the sugar-free Haribo gummy bears? If you do, okay, hold off and I'll read it at some point. But if I read it today, we're never going to make it to the rest of the curriculum in the whole syllabus. So hang tight on that one, but it is fun stuff. Okay, so this is the kind of problem you would get. Does that make sense? And that's what this is used for. So it's not even a lecture theory thing or exam theory. I think it is that. Okay, I feel good about where we are. I feel so good. Oh, here's a question for you. If we ask you what variable a function is most sensitive to, what do you think in English that means? Yeah, Juan.
Where the gradient vector is maximized in one direction?
It has to do with the components of the gradient, but not quite. So if I'm moving in a particular direction, right?
Yes.
Sorry, wait, what am I? Okay, I have a function and I can change it by changing x or changing y, right? How do I know at a particular point which one will change my function more, x or y? Think back to this, right? We have df by dx, df by dy. Whichever one is steeper, that would tell me what?
The maximum or no. What changes more?
What changes most, right? So the variable to which we are most sensitive is the one with the biggest partial derivative. Usually we refer to it as the absolute value of the partial derivative, because we just care how much you change the function. We don't care if you bring it up by a lot or down by a lot. Everybody good on that? So sensitivity. Right, it's like what aspects of a movie tug at your heartstrings, and that's the variable at which you're most sensitive. Whether or not they make you way happier or way sadder is variable for which df by d variable absolute value is biggest. Useful to know. And you find this at a point, right? Because the partial derivatives could be different at different points. If I give you the sensitivity, ask you for the variable to which we're most sensitive at a particular point, you find the gradient to that point, you tell me which component of it is bigger. Figure absolute value. All right. More questions? Okay. There's a bunch of examples that I have written down in the notes, so please give those a look. Now, something that might be worth talking about is if I have my tangent plane equation, and I'm using this to estimate the value of z for a slight shift from my point of tangency, right? Does everyone remember that? So another way I could write this is, again, is the value of z is z naught plus df by dx of p naught delta x plus df by dy p naught delta y. Did I get this right? I think I've covered all of my...
Isn't that z naught plus delta z equals z?
Yes, sir, I like that. That's delta z. Okay, but we want to generalize this. So what is the most general way to write the tangent approximation for a function of multiple variables? And by multiple, for now, I'm just going to call them x, y, and z.
Z naught plus
How do I estimate f of x naught plus delta x, y naught plus delta y, z naught plus delta z? Well, what's your instinct?
what's it called when you like use the data? df dx type.
Yeah, so there's a pattern here, right? We're very good at pattern recognition. Our ancestors figured out what mushrooms not to eat by dying, and also by knowing what properties they were before the people that were watching them saw them die. Yeah?
You're multiplying each partial derivative by its delta.
Yes, sir.
Delta, and then adding it to whatever you started with.
And that is delta f. So f, the new f, is original f plus delta. Does that make sense? So what's the version of me writing this here? Is instead of z equals z naught plus this, how else could I write it? Delta z is equal to this. Are people seeing this pattern? Yeah, fun. I think I have questions. All right. So if I had a function of 20 variables, what does the tangent plane approximation look like? She said. You just said it, right? Yeah. You bet. Is that clear to everybody? It's always the partial derivative in the variable by how much you change. And by the way, you guys, you've seen this before. Let's be really, really lazy about notation for a moment, okay? We're very chill in this room. It's the 1970s. Why is it the 1970s? I don't know. Because I guess people did things in the 70s that would make them there. All right, so, oh man, it's like f, and there's like x, and there's like a delta x. So what do these do with each other? Cancel out. What do these do with each other? Okay, now you might be tempted to say, oh, well, Christian, that just means df plus df plus df. That's 3df. 1 is equal to 3. You know, demolish MIT. The bulldozers are out there already. What stops the demolition company? Is this really df officially?
It's df partial df x.
It's df as contributed to by x. It is a partial contribution to the change in f. It is not the total contribution to the change in f. Does that make sense?
Yes.
Okay. So this, you could call it if you want df, but it really is, it's really df, x. It's the partial differential due to x. The contribution to the change from x. Does that make sense? Okay. Yeah, I wish I could slide this one out, but follow my English here and we'll be okay. O sea, que la clase en español. Si yo enseño esta clase en español, se joda la cosa. How many of you did I lose? That would be really funny and useless, but it's a weird story. It's like I got reprogrammed overnight or something. Okay. So I did say okay in Spanish. Okay. There's a reason I wanted to talk about.
Well, we're talking about all these derivatives. Is there something about maximum? Can we max and min in 3 dimensions?
Yeah, we can. Do you want to max and min in 3 dimensions? Do you want to build a snowman?
I do want to do this.
All right, Elsa. So
Maybe I read the lecture notes earlier.
No, joke's on you because I didn't post those.
No, you didn't know?
Oh, yes,
The
detected.
industry plan here.
Okay. Yeah, they-
The planting student,
okay. So, what? So, no, that was good stuff. So, the reason I say this is also, guys, remember way back in the day when I said that we can write a function that is explicit, right? In the implicit form, so your parents will let you listen to it. This works in implicit form as well. Because what is df by dz when I write this in implicit form? If I choose this particular one, not the other one. This is df by dz, which is
-1.
-1. So do you see how this is all connected?
Yes.
I don't have to necessarily, but yes, it is a thing. So the most general way that you can write this is as the product of the partials with the changes in each of the variables. It just so happens that for a function that is explicitly z as a function of x and y, the partial with respect to z is always -1, or 1 if you do it the other way around. But the negatives will work out in such a way that that is the case. So we are all grown up, and I think that we can do a really cool thing over here. We can write this in vector form. Because whenever you see patterns, and you said the word summation, you know something's up. Anyone want to tell me about a vector operation? What is df by dx, df by dy? Where does that come from? The gradient. So why don't we make this the gradient, and then what operation is happening between the gradient and what? Dot product with delta x, delta y. Does everyone see that? Another way to write that, well, this is the gradient evaluated at p0, very important, right? So another way to write this is grad f at p0 dotted with delta x vector. By x vector, I'm referring to my x and my y components. And this on the right-hand side is delta x. Now, I like this a lot. I like this a lot because it's very general. If you just look at this equation, how many dimensions am I referring to? We don't know, and that's kind of cool. Could it be 2 dimensions? Could it be 3 dimensions? Could it be 27 dimensions? Yeah, right? What's your gradient going to be? It's the gradient of all the variables. Oh, and again, this is f of x vector. This is f of xy or xyz or xy so on. This is the most general way. Okay. Yeah, questions? Everyone good? Okay. So now that we've done this, I would like to do the following. I want to talk about chain rule. Is there a chain rule? We're going to do chain rule in multivariable calculus land. So to do that, I need to erase this. Is everyone okay with that? Objections, questions, tomatoes to throw? Oh, you should stop putting tomatoes. I can't tell you how many indoor water balloon fights I've had. Although we have chinchillas, so we don't do indoor water balloon fights because chinchillas can't get wet. Anyone know why chinchillas can't get wet?
Oil.
Huh?
Oil.
But I want like a complete theory here.
Because the water is so cold that it brings one of their biological functions.
Oh, you mean like chemistry? Oh, interesting. As it turns out, chinchillas have one of the densest, the highest densities of hair among animals. They have like 20,000 hairs per square centimeter or something like that. So if you get them wet, it's almost impossible physically to dry them. So they will get moldy and die. So we don't get chinchillas wet.
I was actually on the there.
Yeah? All right. You know what else? Oh, no. Or yes, depending on the other. All right.
They just died.
All right, guys. So, what is the equivalent of our first derivative in multivariable calc? First derivative. Well, no, no need to overcomplicate it. It's the gradient, right?
Oh.
So not the plus, but just the, or so on and so forth, however many dimensions, yeah? Okay, now you may be asking yourself, well, what about the second derivative? Ooh, so yeah, and the Hessian and all that stuff. But no, let me make sure that I'm, okay, yeah, yes, and I don't want to do second derivatives yet. Why make it more work than it needs to be? Let's go for a general vector value function. So, I'm going to lean on my notes a little bit for this so I don't make a mess. So, vector value function. What does that mean to have a vector value function? What does it spit out?
A vector.
It spits out a vector! So, we have a vector value function. Oh, what is an example of a vector value function that we've used a bunch?
Or
Huh? R of t, yeah, what else? One that we've been spending some time on.
Got it?
The gradient, right? And so how do we know that it was a vector value function notationally? What do we put on the grad symbol?
A vector.
A vector. So we're going to do that. We're going to say more generally that we have a function f, and it is. Ooh, I almost scratched the board. That could have been bad. Okay, grad f. Sorry, not grad f. F vector of x, y. And this vector value function is going to have components that are themselves scalar functions of x and y. Okay, let's describe this in English before the notation suffocates us, strangles us, or finds another way to kill us. What is this saying in English? Someone give it a shot. Hi Lily, can I pick on you? Yeah. Wait, do you say oh sure or oh shit? All right. What does this say? This is what?
A vector and
Uh-huh. Uh-huh. So what is the x component of this vector? U of xy. U of xy is a function of x and y, right? So what's an example? Let's do examples below it in yellow. Sorry to rip to whoever's water bottle that was. So maybe this is going to be x plus y, and this one is x squared minus y squared. Can you imagine that being a function? And so at every point xy, what do you get? A vector, yes? Okay.
Oh, it's a field.
Ooh, it could be a field. I like fields. Which are VR with a field at the opposite. So this is a vector value function. And the question then becomes precisely, we know how to take derivatives of scalar valued functions of multiple variables. What is that called? The derivative of a multivariable function. The gradient, yeah. But how do we take the derivative of a vector valued function?
The derivative of the first two exact components.
Say again?
Derivative of the first component and the second component.
Exactly, derivatives of each of the components. But, oh wait, fun, this is a really good way to put it. Do you agree with me that each of the components is a function of two variables?
Yeah.
So in order to take the derivative fully, what do we need to take the derivative with respect to?
Partial.
Partial with respect to x and y of what? Of u and the v of each of the components, right? The derivative of a vector valued function with, what do I want to say, with n components and m variables. Maybe I'll make this an m and an n. It doesn't matter a whole lot until we actually start doing it. But maybe you see where I'm going with this. How many components do I have?
Or, no, two.
How many components does a vector have? Two. How many variables across the board exist? So how many possible combinations of components and derivative can I take? Four. What's this making me think of?
And matrix.
A matrix. Yes, we're going to enter the matrix. This is me putting on my neo-glasses and saying, what if I told you that derivatives can be matrices? So let's do that for a moment. This is where I'm going to check my notes so I don't screw up the notation.
Do you learn this from your homework, Jacobian?
Don't want to what?
Do you learn this from your homework, Jacobian?
From the, yeah, Jacobian, yeah.
Was he a real person? Or what type of
Yeah, his name was Jacobian, as it turns out. People think that his name was Jacob. No, I'm messing with you, I don't know. All right, so, guys, so formal definition. For a vector valued function, f of xy is equal to u of xy, v of xy. Guys, let's remember something. Notationally, remember, writing it as a column vector versus writing it with the angle brackets are the same thing. Yes? Okay? This is a notation you will be more likely to see in 1806, as it turns out, and this one in 1802. But they work together very well. Okay. So for a vector value function like this, the derivative is called the, what color should this be? Oh my God, I just had blue chalk, how'd you know? Is called the Jacobian. Wow, yeah. He's in his divination era. Okay, is called the Jacobian. And it is the gradient, is the gradient of each of the elements. By elements, I mean the u and the v. So, let's keep working this out. Can I erase this? Yeah? Okay. Okay. Blue for Jacobian. I wish there was a color set with a J. Orange. And then we could do the Jacobian in orange. Here we are. Is this blue enough? Can you all see the blue?
Yeah.
Okay, cool. I wish I had like more neonish blue, but that's okay. Okay, so again. Wait, can you? Is it not too dark? You guys are okay. So f of xy is equal to u of xy, v of xy, and j, the Jacobian, the derivative of f of xy, is the Jacobian of, again, u of xy, v of xy, and that is, brace yourself, it is a matrix whose rows are the gradients. So grad of u of xy, grad of v of xy. Does that make sense?
I see the vision.
You see the vision? Hi.
What is the v vector for?
What is the v vector?
Yeah. Is
Of this, or the grad of this?
Not the other one. Is that grad times?
Yeah, oh no, that is just grad of.
Okay.
Yeah, when you have the grad next to it without it, that's a good point. You'll get grad times at some other point later on. But yeah, grad of means take the gradient. Because u, the x component of this vector, is a function of both x and y, correct? So this is the gradient of it. So let's do a quick example. We'll just plug in some numbers, right? Let's say, what's a
F of xy is equal to u being x plus y.
okay, and b is, x squared minus y squared, right? We had done that one before? Okay, so find the Jacobian. You use the little marking boards if you guys want, and find Jacobian. Okay. Really quick, how many elements should that matrix have? 4, yeah? It's a 2 by 2 matrix.
Wait, what if it's not the same amount of variables? Like
Then the matrix is no longer square. Excellent question. So like, let's say that you had a vector value function with 2 components, but they each depended on 3 variables.
Yeah.
So what would the dimensions of the matrix be?
3 by 3.
2 by 3, yes.
Oh, 2 by. Oh yeah. Okay. What
Yeah.
about like? What if it's like 1 one has x, y, and the other has x. Is that
Oh. Then the one that doesn't have a y dependence, its partials with respect to y are
zero?
0. Yeah, excellent question.
But you'll always get a square root of Jacobian because the del is the same now dimensions of your
Oh, but actually Vaughn just.
Oh, it's not, they're different.
Yeah, you can have a vector value function of 3 variables but only has 2 components.
This is not very
Yeah. All right. So we know it's a 2 by 2 matrix. Guys, what's the first step to solving this problem? What is it? What do you already know how to do before you put it into a matrix? Yeah, take the partials, right? So this one is u. This is u, not u. And this one is v. So what is the gradient of u with respect to x, y? 1, 1. What is the gradient of v with respect to x, y? Wait, 2x, 2y, almost, and there's fix one thing. 2x, 2y, no, right? Yeah, 2x minus y.
I didn't get it.
Anytime you say it, he's it.
All right, guys, so we found these partials. What's the Jacobian? 1. What goes here? 1 or 2x? Which one? 2x or 1? Why? Find me.
Your x is staying in one column.
Yeah, it's the gradients of the rows. 1, 1, 2x minus 2y. Congratulations. That is your gradient.
Did it!
And, you know, if you want to write this with the notation, it's ux, uy, vx, vy. Or, equivalently, du, dx, du, dy, dv, dx, dv, dy. Okay. Yeah, I know.
Wait, can we go back to that question?
Oh, yeah. This one?
Oh, yeah. Sorry.
That's okay. Let's just
So that
apologize.
function like up there.
This one?
In the extent of the other word.
Yeah.
Like,
Oh, that one, yeah, the explicit versus implicit,
X
yeah.
squared is Y squared Z. Is that a scalar function? That's not a vector.
That is not a vector value function, excellent point. So that could be a component of a vector value function, but it
We
is
can
itself.
turn it into a vector value function by using implicit. Maybe I turn
Well, no, but you turn to implicit, it's still a scalar. Right, you put a scalar to the other side. All right, in there, you good? Okay. Guys, questions? Okay, so the way that we refer to a Jacobian, I need to be very, very clear here. This is a notation that I use because it'll help us stay organized, is we are taking the partials of what with respect to what? We start with u and v and we turn them into x, y. So I would write this as j uv to xy. Because think about it, when we write derivatives, we say df by dx or dy by dx, right? So this is basically notationally the same as saying d uv by dxy. I did not drive that home enough, but now I did. And there will be time to drive it home further. Okay. So that duv dxy, that's related to this. What I really mean for this is to be this. Okay. So that's the Jacobian. And believe it or not, the Jacobian works in a really cool way because let's say that you wanted to find, let's say that x and y were themselves functions of other variables, t and s. So now we have following, you guys gonna kill me if I go 2 minutes? No? Nope. Okay.
Oh, wait, allow it. Oh, you sold it.
All right, so we'll do more of this both in workshop and on Wednesday. But let's say that you have f, which is a function of x, y, and you have that x itself is a function of t and s, and y itself is a function of t and s. And I asked you, df by dt and df by ds. The question is, how on earth would you go about doing this? Yeah? Chain rule. This is chain rule. I don't disagree.
Or
No, Kiddo, what's up?
you could plug it in into your f of x and y equation because they're just equal to each other, and then you can just subtract the derivative after that.
I think what you're saying is what I'm about to draw.
Yeah.
I think. All right. Let's say that I want a df by dt. What affects f? X and y, right? What affects each x and y? T and s, right? So this would be df by dx, dx by dt, but is that my only contribution to f? No. Plus?
df dy.
Okay. Let's keep going. What if I asked you for df by ds? How would I do that? I would do df by dx, dx by d, plus df by dy, dy by this. Are there any other dependencies between variables that I'm not capturing? As it turns out, no. And what I'm going to say, but not prove yet, is that all the derivatives you could ever need come from multiplying together the matrices of the Jacobians. Right? Because you're multiplying partial derivatives, right? So think of this as well, don't think of this, but we will see how this is the result of matrix multiplication. That each of these derivatives is the result of multiplying the Jacobian that takes you from uv to xy, and the one that takes you from xy to t and s. That's the multiplication of those successive Jacobians is like you're chaining them together. You're multiplying together, that's chain one, three, or in the multivariable calc. Okay. This is meant to be vague because I don't want to be here till 12:30 if you all should be eating instead. But are there any questions? Are people good? Okay, please bring the whiteboards and erase them, bring them to the front, and the markers, please. And I'll be here if you want, if you have questions. Okay, let's see. Okay. So we have a function that is now giving the scalar vector. So the function gives the scalar object, so it's not like y is x plus 1. The function gives you a vector object, is like that y is x plus y comma x plus y. That is the vector. You Christian, when I write that, hey, see that? One way to do that is adding the little angle brackets. Or I do a comma. So now it's not a scalar function. And the code is how do I scalar function? And the question about how do you do it? Well, how many components does this vector have? Two. How many variables is each independent? Two. So you need all possible combinations of components and variables. So the x component and the x component y derivative. The y derivative, and that's what this is.
Yes, like they're all
So, in fact, sorry, x component x derivative, x component y derivative, that's called the gradient. So it is a matrix whose rows are the gradients in each of the components. Or in other words, this.
Why is that?
U by dx, U by y,
Why don't you do
and this I find a good way to keep it on.
Thank you. Yeah.
Yeah, take care.
Why do you get
It makes sense on paper.
There's a little bit of a reality distortion too. Yeah. No, he said there were a couple things that he said. I should have chilled out a little bit. So don't feel too bad. But yeah, don't feel bad.
sorry, you're.
Warnings will be posted somewhere.
What is your plan?
But also the, ask questions. How are you
Or
doing?
is this the?
Or warning. I'm picking up on that.
So when you go,
On the one hand, it's okay to say food camp and the semesters, but we're not on less.
usually,
I guess, how do you get
Have you
this?
seen one of
Did I already tell the story of how
where they open the book and it's just like,
how did I get the whole thing?
Yeah, like this.
putting too much weight on how you're,
Let's see. Oh, not that.
taking this too seriously somehow is like enrolling in an extra student to place classes. If you can believe it. So, but I think people telling someone else to chill is pretty useless advice. So what can I say?
so I thought
What can I say is, utilize the resources. So if you're not, you're going to spend 2 hours talking to
well, you get a matrix, but
that's good.
if there'd be another component,
And number two, when you're doing a problem,
like,
if you get the concept, everything else will fall. Today I gave a selection,
the derivative of this week.
but I trusted myself, and that ends up being worth a lot more than just knowing. So I don't know what to do. So we just don't have deadlines on assignments. So
Yeah,
it's really sad.
I'm just so worried, just like, I feel like I get it.
So,
Because I think
So
that
like you,
as Christian
no,
religion,
it's
it's like,
y, x is
like
like
it
this,
explained
y is like this, right?
I just
Oh, when you cross.
Then make it-
just spiraling worse. and
Yeah,
worse.
and you don't have time to review the concept because you got nothing.
I mean,
Yeah,
I was
that was me
thinking-
doing interface as well.
Okay.
Just a chunk of my camera.
That's
Some of these things will take a little bit of time to just sort of simmer. Something also worth noting,
square.
exam questions are not single here.
Uh-huh.
And you might stretch yourself so well during these sets that
Why is
that these anyway. And it's a bit like going to a real world job after MIT.
You just put the gradient,
Like,
and the gradient is this, that's it.
there's a little bit of that.
I guess, are you more generally aware of like the determinant as like how it relates to transformation?
Transformation is saying is, I need to give you advice.
Oh, that's what it
That
is.
is useful.
Because that's what our determinant is.
What
Because
do
if
you
you have
use for
two,
it?
this is a transformation matrix, but it's corresponding
But
to
why didn't you call
very
it like?
specific
I
type
see
of
what you mean.
transformation.
So theoretically,
I
take two really small
So
vectors.
Jacobian is basically literally, you're taking the derivative of the vector function.
They were gonna be, they were.
Oh,
And
units,
it's just like, they don't.
and that
They were.
applying the matrix determinant on the
And then.
the
I
magnitude
just don't know.
gives me the transformation. The
Like they, basically,
what's the word for how much something changes? Yeah, the factor by
To be
which
used to construct
is
that
changes. Although, like, maybe it might be like 20 times
it's
less.
And that is far from worse.
The yeah,
it's very simple thing.
yeah, that's, that makes, thank you. Yeah,
Experience will get you
because,
closer to
so the reason why it's dx and ui is because you want super small. Well, you can just
Promise.
combine this,
Promise.
x, y.
That is the case.
Oh wait, no,
It's
units.
not very slow.
T and.
Well, you can say this.
You probably make a really good teacher.
If I have a
because
square
it's
and x, y, I'm gonna transform it into uv and the scaling factor.
So you're saying like you transform x into u,
Because
or
when you're
y
defining
into
that comes in,
v.
it's actually just making-
Well, then you just transform, oh, I guess.
That's it. There's a chance one day someone's
It's like, you have like the unit square, you're saying like the area formed by the unit square, multiplied by a factor of j gets the area in UV.
And that can be applied to any general area.
You know me well.
Yeah. So therefore, this statement
I did, I didn't
meaning that
understand,
for any,
like, trying to
meaning
fix
that
it.
even if you shrink them down to the x and y, that statement holds.
Because to a certain extent,
That
I mean,
makes
it's
sense. So if I have like,
and it's
But
tricky because you also
it's
have
like,
four other
I
classes.
I don't see by how or scale it. Like this statement will hold.
I don't know the project. I don't like it. This is weird.
If I have two vectors and I make or no, wait, what's?
This
I'm
is
very
a
comfortable
scale.
with
little
it
step
and
It's
team
what,
dynamics.
give a scale, this is not, give a scale, this
Like,
is the
what is
direction,
the
this is the
That
scale.
question, I don't very well.
This is the scalar input.
Oh,
We have
I
a
see.
scalar.
Anytime we go with it.
Like, I think.
Part of it's not, it's not, in terms of what the contract is. It's actually.
Angles.
I get what you mean, but, so then we can only apply
There's just so much value to just having.
Yeah, like, I don't actually have the retrostructure.
I use it to
Just pull that in.
to
You can actually qualify it.
but none of the,
okay stuff. And like if I was
the general intuition
for
behind the
the
transformation
Well,
is
it's
that.
just basically
not the
trying
wisdom
to
that I think I have.
translate
I probably told you to generate practice swap.
And
That's an
that
issue, real people,
determinant
which are better, but.
scale. And that's why the determinant of
And the other thing is, to be honest with you, talking about
transforms your
space,
space. Yeah.
especially when you're on, because when you're only, like, all that.
Yeah, its nature is.
So usually when you do a practice.
Okay, it does
You see the answer.
Why does it
I
transform?
could see this, maybe that's not the connection.
Because of how we define the Jacobian, like Delhi and Delhi.
Yeah. Find out why.
Yeah, 'cause like,
Questions and-
Advanced Christian thing, these are like.
I'm not one of these people who's gonna give you general advice, and be like, yes, that works for me. You're gonna find the same
Like
formulation.
percentage of entry.
Oh, so like
You're-
for X, Y, how much will you change?
Yeah,
So
so for each.
the fundamental thing is
giving like.
what that final
rate of
formulation
change,
looks like, it's trusting that
at that
it
perspective.
exists. Because it
So like,
you know,
as a result, if you like,
You know me.
apply the Jacobian to a vector, like what happens if each one change linear combination at these different points based on the rates of change.
We got it back.
Oh,
Evidence
that's why
killing
the
us. Evidence is gonna kill the
As a
world.
result,
Any time on Saturday,
the Jacobian
and I'll
contains
show up
information
with
like
my
how to every direction.
Exactly.
Perspective. And when you.
That's what you
when
have
take
for.
J and you like perform it on a vector,
No, I enjoy you.
then our resulting like output is gonna be a linear combination involving all of these rates of change. So that new vector has all of the information about how f is changing
Yeah.
through the Jacobian. So that's why our output sort of behaves
no idea it was that way.
like in a correspondence with how f is actually changing.
Are we gonna do the path thing where like we trace that?
No, piece of this week is your mention.
No.
Oh, yeah,
Because that's the use of that.
Yeah, yeah.
I feel like in essence, I don't know.
I should post it. I'm writing the exam, so I'll probably just take some of those questions. Yeah.
Oh, no, I mean, just in general.
Cindy, what are the
But
level
yeah, no,
goals?
I think it'd be
Oh,
cool.
they're the back.
That would be good. That
I-
makes a lot of sense.
I actually like you were one of the first people
The more that
to
we
use it and send it back.
I think that was like, that and diagonalization.
We're the left curves.
Yeah, oh yeah, actually, that's what you do when you get an MRI, is the cross sections, yeah.
That's good. That makes
Thank you.
Yeah.
Yeah, it's easy.
You and I forget to turn off the
Oh, but I think for that you do put this though, because like when you do, you're doing the picture.